Hello. In the last lecture, we looked into the linear array, and for the linear array we saw how the maximum radiation can be calculated in the main beam direction, as well as how the radiation can be calculated in the minor lobes, which actually are also known as side lobe level. We also looked at the expression how to find out the null direction and then how to calculate the first null beam width. Then we looked into the different thing, and now let us just look at the again one more time the radiation pattern of the array. So, we can see here that the array is reducing down to a certain value, but there is a possibility that if we increase the psi value to a greater value, for example, if psi increases beyond 180 degree, it goes from 0 to 180 and then it becomes, let us say, 360 degree. At psi equal to 360, again the radiation will be maximum. So, if that value happens somewhere in this domain for some other value of phi, that can give rise to grating lobe. So, we should always try that psi should not become 2 pi, because if psi becomes 2 pi, then again we will have a maximum radiation. So, that maximum radiation is known as grating lobe. So, we need to avoid the grating lobes in all the situations. So, we have seen that psi is given by this particular expression, and this should be less than 2 pi, and where phi m is the direction of maximum radiation. So, just to recall, if phi m is equal to 0 degree, that will be an end fire array, and when phi m is equal to 90 degree, that will be broadside array. So, over here the condition is that psi must always be less than 2 pi. So, if we simplify this, we can see that d by lambda should be always less than this term over here. Now, the maximum value of cos phi, as phi varies from 0 to 360 degree, can be minus 1, and over here the maximum value of this again can vary from 0 to 1. So, we can say that if d by lambda is always less than this, which is the maximum of the denominator. So, that will be 1 plus the amplitude of this here. So, if this condition is satisfied, psi will never ever become 2 pi for any given value of phi m. So, that leads to a condition for broadside. What is phi m? Phi m will be 90 degrees. So, cos 90 is 0. So, d by lambda should be less than 1. So, if we are designing a broadside array, d should be less than lambda. But if we are designing a end fire array, in that case phi m is 0. So, cos 0 will be 1. So, this should be d should be less than lambda by 2. And this is an important thing, that for end fire array d must be less than lambda by 2, and for broadside d should be less than lambda. And if d is equal to lambda by 2, it will give rise to the grating lobes. In fact, we can actually look at the very first example of the 2 element which we had seen, that in this particular case, if you see that this is the end fire array and the distance taken was d equal to lambda by 2, and that is why there is a grating lobe on this direction. Had we taken d less than lambda by 2, then this grating lobe would not have occurred. So, you have to remember that the d must be less than lambda by 2 for end fire array. Okay. And if you are scanning the beam, so let us say the beam is being scanned to say 60 degree. So, cos 60 will be 1 by 2, and that will give rise to that this is 1 by 2. So, that will be 2 by 3. So, d by lambda should be less than 2 by 3 for a beam maxima to be at 60 degree. So, that is why majority of the time when we design a broadside array, invariably we take d as maybe 0.5 lambda or 0.6 lambda or 0.7 lambda, but never close to lambda. Similarly, when we design an end fire array, majority of the time we take d less than 0.25 lambda or maybe 0.3 lambda, but never close to 0.5 lambda. So, now let us see what happens when one power to one of the element is missing. So, here is the case when all the 5 elements are fed with equal amplitude and equal phase, and in this particular case, just to tell, so there are 5 sources, each source is spaced at lambda by 2. So, there are 5 elements. So, from here we can just look at, so this array factor is very similar to the array factor which we have derived earlier, and for this case you can see that the beam here is going to at 0.71 at after a 10.4 degree, here this angle is varying from 0 to 90 degree. So half power beam width will be double of this here. Now instead of all the 5 elements, let us say that if one of the element here is not getting the power, so array length still remains the same. So one can see interesting that this particular beam width remains almost the same, but what is the difference? Side of this the nulls are almost disappeared, and we have a side radiation which is actually fairly high. So if you try to calculate directivity always using the expression d is equal to 4 pi divided by theta e theta h, it is not a good idea. You should also look at what is happening to this. So compared to this pattern and with this here, the directivity of this is actually higher compared to this, because unnecessarily radiation is going in the undesired direction. So over here now there is a different situation. The central element is not fed, but all the other elements are fed. Now if central element is not fed, let us see what is happening. This one has reduced from 10.4 to 9.2, but the side lobe level has increased drastically. So again if we blindly apply the concept of that half power beam with reduced directivity will increase, then this will give us a wrong answer. In fact, the directivity here is reduced compared to this here. Why? Because lot of power is getting wasted in this particular minor lobe, which has increased significantly. So well, let us just pay little attention here. So what we are doing, we are putting 1 1 0 1 1. So if the central element is 0, what we are noticing, side lobe level increases. So now think other way around. So if the central element is fed more power, then what will happen? Side lobe level will decrease, and over here half power beam width actually reduced. So but if we use more power here, then half power beam width increase. So we will see in the next slide what happens if we actually use a non uniform amplitude. But let us just take another one last case here, that the last element is not fed, and when the last element is not fed, this whole thing is equivalent to 4 element array, and we know that for 4 element array the half power beam width will be more, and there will be just one complete side lobe, and that you can see from the array plots. So let us just now see what happens if we use uniform amplitude or we use non uniform amplitude. So again let us take a case here, there are 5 elements are there. So for these 5 elements equal amplitude is fed, and the spacing between the element is lambda by 2, and if the spacing is lambda by 2, total length will be 2 lambda from 1 to 5 element. So for this case we can see that this is the radiation pattern, and side lobe level here would be less than minus 13 dB. If we use binomial distribution, what is binomial distribution we will see in the next slide, but over here let us just look at the distribution here, where we are feeding at 1 4 6 4 1. That means the amplitude fed over here is 6 times more than the end element, and in this case if you see there is absolutely no side lobe level. So that is a great thing, but there is a difference is that the half power beam width increased from 23 degree to 31 degree. So even though there is a no side lobe, but just because half power beam width increased so drastically, the gain of this antenna is relatively less. And I want to tell you here, except for 3 element binomial, practically binomial distribution is not used. So generally a practical case is somewhere over here, even though term says optimum. In this case here the levels are 1 1.6 1.9 1.61. So that means the central element is approximately twice of the power fed compared to the end element, and in this case you can see side lobe levels have reduced, which is less than minus 20 dB, but the half power beam width here is slightly more than this one here, but it is less than binomial distribution. So, gain of this will be slightly less than this, but side lobe levels are improved further. This is just one case. You can actually think more like from a grating lobe point of view, that if only two end elements are fed, what really would happen? It is like a spacing between the element is now equal to 2 lambda, and we had seen that for broadside grating lobe happens if the spacing between the two element is lambda, but here it is 2 lambda. So, if there are 2 lambda, now there are 2 grating lobes which have come. So, generally speaking, this is not desired except for an application where you probably want to send maximum beam in multiple direction, which is very few applications require that. So, in general we should never ever have a situation where spacing between the element for broadside is more than lambda, otherwise it will give rise to the multiple lobes. So, half power beam width may look narrow, but the directivity is much less. So, how do we calculate binomial amplitude distribution? Well, it is something like 1 plus x to the power m minus 1. So, if m is 1, there is only one element, then m 2 3. You can actually think about something like a plus b square. What is a plus b square equal to? A square plus 2ab plus b square. So, a square coefficient is 1, 2ab coefficient is 2, b square coefficient is 1. If you look at a plus b cube, it is a cube plus 3a square b plus 3ab square plus b cube. But one can actually also do the derivation in a very simple manner. You can actually make like concept of the tree here. So, what we do here, 1 and 1 you add, put 2 here and side 1 goes there. Over here now 2 plus 1 is 3, 2 plus 1 is 3, put that in between, end elements are 1. Next here 3 plus 3 is 6, 3 plus 1 is 4, 3 plus 1 4 here. Going down further, 6 plus 4 is 10, 6 plus 4 is 10, 4 plus 1 is 5. So, now think about if I have to go to even a larger element, suppose if I go to 7, m equal to 7, this it will be then 10 plus 2 20 will be here, 10 plus 5 15 will be there. If I go next, it will go to 35. So, the amplitude ratio changes drastically, and that is why power fed to the end element is very small, and if the end elements are not getting power, it is almost equivalent to having a lesser number of element. So, yes, we do not get any, no side lobe levels are there, but beam width becomes very broad, gain decreases, and hence practically binomial distribution is not used. So, what are the different plots here? Let us just look into it. So, here is a non-uniform amplitude distribution for different cases. The first one here is uniform, that means all elements are fed uniformly. What we have taken here, total number of elements 17. So, here is central element, 8 elements on the right side, 8 elements on the left side, and the spacing here taken is lambda by 4. So, the total length of the array is 4 lambda. So, for uniform, all 17 elements are fed with equal amplitude. A binomial distribution, which we had just seen in the previous one, if we take that binomial distribution, that distribution will look like this here. Now, you can see that the last 3 element 8 7 6 this side and 8 7 6, the power fed to these element is almost close to 0. So, it effectively works more like a 13 element array instead of 17 element, and that is why the directivity of binomial distribution is very poor. So, now these are the two extreme cases, we have two in between cases here. So, we have a Taylor distribution which is shown like this here, just like a Taylor series, and this is the Dolph-Chebyshev distribution here, just like Chebyshev filter which has a maximally flat response. So, these are the different cases here. In fact, if you try to approximate, you can almost approximate this as a roughly a triangular waveform with some pedestal. This can be almost thought of as a sinusoidal waveform with some pedestal. So, there is a similarity between triangular and cosine function. So, let us just see if we actually use the distribution which is given by these here. So, we again as before uniform is over here. If we have a cosine distribution, that will be the cosine distribution. A triangular distribution is given by dotted here, that is a triangular distribution, and this is a cosine square distribution. So, if you actually see cosine square distribution kind of resembles with the binomial distribution. So, that is why this cosine square gives us the lower side lobe level compared to the uniform thing. So, actually speaking, instead of using many a times those Dolbeschef or Teller, it is actually simpler to use triangular distribution or sinusoidal distribution, because it is easy to derive these expression. So, here is the plot here. You can see here uniform, triangular, cosine, cosine squared. So, what we have here, distribution is given, that is I0, and triangular will be given by this cosine. I just want to bring to your attention that we started with a linear array which has a number of elements, but if number of elements are increased drastically and if we reduce the spacing between the two elements, let us just take a case here. Instead of 17 element, if I say that the distance is reduced from lambda by 4 by 10 times, let us say lambda by 40. So, that means we will have very large number of element, but since the distance is reduced, I will use 10 times more element. So, it almost looks like a discrete array is now close to a continuous element array. So, here we are actually showing, instead of writing an array factor, we are defining the term space factor. So, array factor limiting condition is space factor. So, array factor in which d is reduced to a small value, n increases. So, we know for array factor what we had seen, the function was sin n psi by 2 divided by n sin psi by 2. Now, if psi is small, because d is small, then n sin psi by 2 will become n psi by 2. So, really speaking, it becomes a sinc function. So, looking at uniform, all elements are fed with uniform, or if it is a line source, the current is uniform, and for this the array factor response will be a sinc function. If it is triangular, that is the triangular distribution, this is the cosine distribution, this is the cosine square distribution. Now, these currents can be well defined with the equation, and for that then space factor is also very well defined, and you can calculate space factor for these cases. So, it is easy to do the next derivation, which are as follows. Now, we want to calculate the, let us say, half power beam width. We had seen earlier that half power beam width is given by this expression, but for triangular you can see that the half power beam width has increased, cosine it has increased this. So, that increase in the half power beam width leads to the lower gain, but what is important first to look at is the side lobe, because that is the reason we use this here. So, for uniform, if we get a side lobe level as say minus 13.2, if we use triangular, side lobe level drastically reduces to 26.4, cosine distribution is in between, and cosine square reduces the side lobe level to below 30 dB, which is minus 31.5 dB. So, now looking at these numbers, so we can see that if we use this distribution non-uniform, then we can reduce the side lobe level, but one can also see half power beam width increase, which results into the decrease in the directivity. So, this is the directivity factor for large L. So, this is 2L by lambda, which we had seen for uniform. So, now that is reduced by a factor of 0.75 for triangle, by a factor of 0.81 for cosine. So, you can see that the directivity has reduced. So, that is why many a times what is actually done, that instead of using a simple cosine distribution, we actually use a cosine with a pedestal. So, what we can do, instead of using amplitude from 0 to 1, which is normalized here, you use let us say 0 to a constant one, and then from a you make a cosine function. So, that looks somewhat similar to the Dolf-Chebyshev function here, or we can use a triangular distribution with a pedestal, and if we use triangular distribution with the pedestal, it almost looks like a close to Taylor distribution. So, we can reduce the side lobe level by using this pedestal, and also since this element here is actually being fed 0 power, so that is why it actually array in effect reduces from 17 element to 15 elements. So, if you provide a pedestal, that means some power is fed to the last 2 element, and hence you will get a little better directivity compared to these numbers here. So, by providing a pedestal to cosine, we can increase this factor from 0.81 to maybe close to 0.9, or maybe 0.7 can be increased to 0.8 or 0.85. So, that will reduce the side lobe level slightly, but also decrease the directivity also slightly compared to the uniform array. So, now instead of here we had taken a simple space factor for the aperture, the proper aperture line source that can be extended to the square, but if we use a circular aperture or circular array, what we see now here, if the distribution is uniform, a radial taper, it is going from 0 to the outward or the radial tapered square. So, if we use circular aperture, what we see here, that for uniform distribution also side lobe level is minus 17.6, whereas for uniform square aperture it was 13.2. So, from 13.2 it has reduced to 17.6. So, what is the reason? So, you have to think about a square aperture as a complete thing which is fed over here, whereas circular aperture is in between. So, if you think about a square aperture superimposed on a circle, what we are seeing is that the end element is not being fed, and also the next to the end element now are actually getting less excited. So, in reality what we have done by using a circular aperture, there are no end elements only. So, that means there is a no power going to the end element, and hence it is kind of a natural amplitude taper. So, since there is a natural amplitude taper here, side lobe level is reduced for all the direction. So, it is actually sometimes good to use a circular aperture or circular array, and here I just want to tell that these array theories are very, very important when we are going to look at all the other cases. For example, when we discuss next topic, which is a microstrip antenna, we will see that it is an array of 2 slot antenna. When we discuss about, let us say, horn antenna, for horn antenna we will see that in one plane we have a uniform distribution, and in the another plane we will see that it has a cosine distribution. So, in both the planes you can use the array theory, or you can apply the space factor concept, and simply by using this concept we can actually find out what will be the radiation pattern, let us say in this plane if it is uniform, or we can find out what is the radiation pattern in this plane if it is non-uniform. So, this array theory will be very, very useful. The same thing will be also applied, let us say when we talk about a reflector antenna. So, again a reflector antenna has a circular aperture, it may be a parabolic, but the outer here is a circular. So, we can actually apply again the circular amplitude concept and find out what is the radiation pattern in the 2 planes. So, array theory becomes then space factor, and it can be applied even for a helical antenna. When we look into the helical antenna axial mode, we will see that helical antenna normally follows increased directivity area concept. The same array theory will be also applicable to log periodic antenna and Yagi-Uda antenna. So, I want that you people should study this array theory very thoroughly. Now, we will just quickly look into the planar array. So, if we are going to the planar array, what we have now, array elements are there in both x and y plane. So, it is a combination of linear array, but now it is linear array. If you think about, this is a x direction, this is a y direction. So, you think about there is a linear array over here of m element, and then this linear array is getting repeated by n times. So, the total number of elements are m multiplied by n. So, finding array factor is actually very simple. All we do it is, first we find out the array factor for this linear array, and that will be nothing by given by this term here, 1 by m sin m by 2 psi x. What is psi x here? That is corresponding to the elements going towards x direction. Now, we can apply principle of pattern multiplication. So, this entire linear array can be thought of a single element, and then that single element is getting repeated n times. So, we have now a linear array of this combined thing over here, here, and we can now apply n element array which is over here. So, now the difference compared to the previous case is that in the previous case we had only one psi term, but now we will have a psi x term. So, psi x is nothing but given by this expression here. How do we get this expression? Let us say we are trying to find out the radiation pattern at far away distance r. What we do it is, we take a projection that on the xy plane. Now, since this angle is theta, the projection of that on this one plane here will be multiplied by sin theta. So, you can see that sin theta is coming at both the places. Now, when this is projected down here, if we take this particular thing along x axis, then we need to multiply by cos phi, and that is what is done over here. And if we multiply this along the y axis, now it should be multiplied by sin phi, and that is the term over here. And what is beta x and beta y? Well, it is same as delta earlier. So, that is the phase difference in x direction, phase difference in y direction, and we can find the phase values in x and y direction simply by making psi x psi y equal to 0. So, if we make that 0, we can find the value of the phase shift. So, for any given value of theta 0 and phi 0, we can find out. So, let us say we want the beam maxima at theta 0 equal to 10 degree, and we want another one phi at maxima at phi 0. So, our angle is given. See, remember theta 0 phi 0, both of them are 0, that will be broadside. So, now if theta 0 is equal to, let us say 10 degree, that will be from here 10 degree, and if phi is say 20 degree, that will be from here. So, that is how you look at. So, I want that you do little practice now. So, find out as a problem, find out what is the phase shift for, let us say theta 0 equal to 10 and phi 0 equal to 20. You can take the spacing to be equal to lambda by 2 for both the cases. So, we will continue from here in the next lecture. Just to summarize, so today what we have seen, we started with the grating lobe, how the grating lobes can be avoided. Then we looked into it that even if one of the element is not fed, array will still perform, maybe not to the optimum level, but still connectivity will be maintained. And after that we looked into the different cases of the non-uniform amplitude. So, we saw that we can use a triangular distribution, cosinusoidal distribution or cos square distribution, or in parallel we can use binomial distribution or Chebyshev or Taylor distribution. By using non-uniform distribution, what we have achieved is we can reduce the side lobe level, but at the expense of decrease in the gain of the antenna. And then we looked into how to calculate the array factor for planar array. So, in the next lecture we will look into different examples of planar array. We will look into rectangular array, square array, triangular array, hexagonal array, circular array, and so on. So, okay. Meanwhile, please do some practice and do some design. You can even look into a simple design. Let us say that we want to design an antenna array for example a rectangular array which should give me a beam width of, let us say 30 degree in one plane, and in orthogonal plane I want beam width to be 20 degree. So, look into that, how to design that particular array. Thank you, and we will see you